Hello everyone. In this lecture, I will discuss about the temperature stresses in the composite bar. In the previous lecture, we already discussed about the temperature stresses in a bar. Here, once again, we have to revise the concept. First one is bar AB having length L and free to expand due to the temperature rise, that is the capital T. When a member having free to expand, there is no thermal stresses which will be generated in the member. Reason is, we know that when the stress is the resistance offered by the deformation. Here, there is no resistance to the deformation and the member is freely expanding. So, here there is no resistance for the deformation and also no stresses will be generated in the member. And we know that when the deformation by the temperature rise capital T, that is delta T equal to epsilon T into capital L. So this is once again we have to write down the deformation by the temperature rise, that is the delta T equal to the alpha TL. Here alpha is the coefficient of the thermal expansion. Now see the second condition, that is bar AB having length L and fixed at the both ends. So here fixed at the both ends and rise in temperature capital T. In this condition, stresses will be generated in the member. Reason is, due to these fixed supports, the resistance is offered to the deformation. So actually the member will be takes place deformation when the freely expanded. So here actually deformation is possible. So when the member having the free to expand, but due to the fixed supports at the ends, member is not expanding. So here resistance is offered by the member against to the deformation. So obviously, when the member is resistance offered by the against the deformation, we know that when the stresses it will be generated inside the member. Now the question is, which type of stresses it will be generated? It is the tensile or compressive. See here, member is free to expanding. Let us consider this is the free expanding, that is the delta. So due to the temperature rise. But due to the fixed supports, these fixed supports are try to contract the member against the expansion. So fixed supports are contracting the member. We know that when the due to compressive stresses in the member, it will be contract. So here type of stresses it will be generated are the compressive stresses. So I think so understand the concept. So if it is the freely expanding mean, so deformation is possible. But due to the fixed supports, these fixed supports are try to contract this deformation. So contraction is taking place due to these fixed supports. And we know that one contraction is possible. So when the stresses, type of stresses it will be producing compressive stresses. With the compressive stresses only, contraction it will be takes place. So this is the stresses it will be compressive when the change in temperature is positive. Similarly, it is the negative in nature. Type of stresses it is the tensile stresses it will be generated when the temperature is negative, which means decrease. And the value of these compressive stresses, these stresses is the alpha TE. So already we discussed how we get this formula. So here I have to remember the two formulas. One is the expansion, deformation. So deformation of the body when the free to expand. So here delta T equal to the alpha TL. And second one is the type of stresses it will be generate. The value of the stresses is sigma T equal to the alpha T. So these two formulas you have to remember. Now see the temperature stresses in the composite bar. When a composite bar consisting of two materials having different coefficients of thermal expansion is subjected to temperature, opposite kind of stresses will be set up in the two materials. Let's see the details. So let us consider here composite bar having the two materials, which is steel and copper, and also we know that one the coefficient of thermal expansion of the copper is greater than the coefficient of thermal expansion of the steel. So thermal expansion of the copper is greater than the thermal expansion of the steel. So which means here delta Ct, which means free expansion of the copper due to the temperature rise, is greater than the delta St, which means free expansion of the steel due to the temperature rise. So this is we have to observe in the diagram. So here, so delta Ct is greater than the delta St. So what do you mean by delta Ct mean? So free expansion of the copper due to the temperature rise is greater than the delta St. So what is the meaning of the delta St mean? Free expansion of the steel due to the temperature rise. And one more thing you have to remember, if the two materials are indivisible, if the both of the copper and the steel are behaving like individual materials, copper will expand more than the steel. Why means we know that one alpha C coefficient thermal expansion is greater than the coefficient of the thermal expansion of the steel. For example, if the individual members copper will be expand 10 mm and steel will be expand 6 mm, which means let us consider here delta Ct is 10 mm. Let us consider just an example point of view, and here delta St is 6 mm. So 6 mm we have to consider. So here delta Ct is greater than the delta St. Why? Because mean alpha C is greater than the alpha S. But steel and copper, but here steel and copper bar are composite bar, which means both of the materials behave like a single material. So copper and steel will be expand the same amount of the expansion, that is the average of the 8 mm. So here let us consider this is the 8 mm. Here expansion of the copper and the expansion of the steel are having the same amount. Let us consider the 8 mm. So why means, so previously copper and the steel are behaving the individual materials, then copper expansion of the copper will be more than the expansion of the steel. But in this condition composite bars, now steel and copper are behaving the composite material. So which means behaving like a single material. If the single material means here only single expansion. So here expansion will be takes place 8 mm only. So here we have to remember that one copper is freely expanding up to 10 mm if it is the individual material, but here it is expanding up to 8 mm only if it is a composite bar. Similarly, steel also expanding up to 6 mm if it is the individual material, but here steel is expanding up to 8 mm if it is a composite bar. So here we have to understand that one copper bar is contracting due to the temperature stress. So actually 10 mm is possible, but it is expanding only up to 8 mm. So here contraction is taking place due to these temperature stresses. That is, here we are considering the delta C sigma. Delta C sigma mean, so free expansion of the see here. So compression of the copper due to the temperature stresses. Similarly, steel ball is expanding up to 6 mm, but as a composite material it is expanding up to the 8 mm. So this is the delta S sigma. Delta S sigma means expansion of the steel due to the temperature stresses. So here we have to understand that one. The final expansion of the both of the material is the same. So this is the final expansion. Let us consider 8 mm. So 8 mm is the final expansion. It is the same in the both of the materials. Now question is which type of stresses it will be generated in the steel and copper. So this is the very important for the competitive exam point of view. See, in copper contraction is taking place due to this temperature stress. So compressive stresses it will be generated inside the copper bar. Similarly, steel is expansion is taking place. This is the delta S sigma. This is the expansion is taking place due to this temperature stresses. So here expansion is possible in the steel bar. So tensile stresses are generating in the steel bar. And now see from the statics, tensile force in the steel should be equal to the compressive force in the copper. Let us consider PS equal to the PC equal to the P. Here PS equal to tensile force in the steel member, PC equal to the compressive force in the copper. It should be equal to the P. Let us consider this is the equation 1, and we know that from the compactability equation, final expansion of the steel equal to the final expansion of the copper. Why? Because it is the composite material. So with the composite bonding, so both of the materials it will be expand with the equal amount. So final expansion of the steel should be equal to the final expansion of the copper. So that is delta C equal to the delta S equal to the delta. So which is the delta C equal to final expansion of the copper. It should be equal to the final expansion of the steel, that is the delta S, equal to, let us consider delta is the final expansion of the composite bar, and let us consider this is the equation number 2. And now from the geometry we have to observe that one. So delta C, that is the final expansion of the copper, so which is equal to the, so this is the final expansion of the copper, which is equal to the delta CT minus delta C sigma. So this is only delta C. Similarly here I have to observe this is the final expansion of the steel. So here, so delta ST which should be, so delta S equal to the delta ST plus delta S sigma. Let us consider this is the equation number 3, and also we know that one. So previously we discussed that one. Final expansion of the steel should be equal to the final expansion of the copper. So from the equation 3 we have to substitute here. So which is delta S equal to the delta ST plus delta S sigma equal to the delta CT minus delta C of the sigma. So which is equal to the delta C sigma plus delta S sigma equal to the delta CT minus delta ST. And we know that when the, so deformation of the member due to the temperature rise, we know that when the alpha LT. Similarly here we have to substitute this. So delta CT is the, so free expansion of the copper due to the temperature rise, that is the L alpha C T minus, so this is the free expansion of the steel due to the temperature rise. This is should be L alpha S T. So then substitute these values here. We will get the LT into the alpha C minus alpha S. Let us consider this is the equation number 4. And we know that from the, so expansion of the steel due to the temperature stress. That is, we know that one, that is the delta S sigma equal to the, so PL by AE. So here PL by cross section area of the steel and the Young's modulus of the steel. Similarly, delta C sigma, which is expansion of the copper bar due to the temperature stresses, which is equal to the PL divided by cross section area of the copper into Young's modulus of the copper. And we know that one, the amount of the forces, the final force. So PS equal to the PC equal to the P. Previously we are considering that one. So here, so PL by, so delta S sigma equal to the PL by AS ES and delta C by sigma equal to the PL by AC. And also from the previous equation, so we know that when the delta S sigma plus delta C sigma equal to the delta CT minus delta ST, which means the summation of expansion of the steel due to the temperature stresses plus expansion of the copper due to the stresses equal to the, so LT into the alpha C minus alpha S. So this is, so we have to substitute delta S and delta S sigma and delta C sigma values. These values substitute here, we will get the PL by AS ES plus PL by AC EC equal to the LT into alpha C minus alpha S. So here we have to write down the PL, we have to take the common point, then PL into the 1 by AS ES plus 1 by AC EC, which is equal to the LT alpha C minus alpha S. Here L will get cancelled, then P equal to the T, that is the temperature rise, into the alpha C minus alpha S, that is the difference between the coefficient of the thermal expansion of the steel and the, sorry, copper and the steel. So divided by 1 by AS ES plus 1 by AC EC. So this is the forces generated in the steel and the copper, which is, that is we are considering the capital P equal to the T into alpha C minus alpha S divided by 1 by AS ES plus 1 by AC EC. Similarly, we have to calculate the induced stresses in the steel and copper. So we know that when the stresses is nothing but, so forces divided by the cross sectional area. Directly we have to substitute P value in this equation. So we will get the, induced stresses in the steel and the copper. And one more thing we have to remember here. So this is from equation number 5. So this is from the equation number 5. So P by LL here get cancelled. Then P by AS ES plus P by AC EC equal to the T into alpha C minus alpha S. So P by AS directly have to write down the sigma S. Sigma S by ES plus, this is also P by AC, directly have to write down the sigma C divided by EC equal to the T into alpha C minus alpha S. So stresses divided by Young's modulus is nothing but strain. So strain of the steel plus strain of the copper should be equal to the T into the alpha C minus alpha S. And one more thing we have to remember this one. So final deformation. So deformation values. So we know that one, final expansion or final deformation of the composite bar, that is the delta, which is equal to the final expansion of the steel. We know that when the final expansion of the steel is nothing but, so deformation with respect to the temperature rise plus deformation with respect to the stresses. So that is, we know that one. So deformation with respect to the temperature rise, that is the LT alpha S plus, this is already we determined, PL by AS ES. Then here substitute the P value in this equation, we will get the final expansion of the composite bar. So maybe this is the concept how to calculate the forces and the deformation of the composite bar. Maybe you people will be understand, we will be discuss with any example problem. So here just you have to understand the concept, which type of stresses it will be generated. So when the composite bar is made by the two different materials, and how to calculate the this final expansion of the composite bar, and also have to determine the what are the forces is required for the final expansion of the composite bar. So this is the P and delta values here we determined. So maybe you will be understand this concept by explaining with any example problem. So thank you.